Okay, good afternoon. Today we'll continue with examples of CVD and ideal diode analysis. Before that, does anyone have any questions they'd like to get answered? Okay. For those of you attending online, I would not be able to monitor the chat window. So if you have a question, feel free to interrupt and just speak up. Okay. Just be aware there are speakers in the classroom, and so your voice will be recorded. No identifying uh, no identifying names or anything else is recorded, but there are speakers in the classroom, so everybody can hear your questions. All right, let's go to here. And lecture 16, make sure the right place. Okay, so we had stopped here. We had looked at this circuit, and we had just discussed how we can apply a analysis model to analyze the output of the circuit. Okay. First thing I want to point out is that ideal diode, so it's not point out, it's just basically a repetition. Ideal diode model and the CVD model, the constant voltage drop model, are exactly the same, except the CVD model in forward bias is modeled as a short circuit with a 0.7 volts voltage drop. This 0.7 volts comes from the fact that it is required voltage for the diode to turn on. So it's the diode turn on voltage. If the turn on voltage is 0.6 or 0.2 or 0.3, then you would model it as a voltage source with 0.6, 0.2, or 0.3. Okay. The diode turn on voltage is kind of a material property. It depends on the material that we use to build or fabricate the diode. So for silicon diodes, it is 0.6 to 0.7 volts. For germanium diodes, it is between 0.2 and 0.3 volts. And for, let's say, LEDs like gallium arsenide, it is above 1.1 or 1.2 volts. Okay, so it is based on the fact, so it's based on the material that is used to build the diode. If it is not provided, you can feel free to assume your own value. But typically it's just 0.7. Okay. All right, so let's begin this. So in the ideal diode, we'll begin with the ideal diode model. I will go over the ideal diode model just for this example. And then in this example, I will contrast the differences and similarities between the ideal diode and CVD model. And for the remaining examples, we'll only look at CVD models. Okay. So in the ideal diode model, what do? We model the diode either on or off based on the voltage that is applied to it. In this case, we are applying voltage V in to the diode via a resistor R. The resistor would have a voltage drop, but we're not concerned with it right now. So we would say if V in, we have two cases, if V in is less than 0 or is greater than 0. Remember, ideal diode model only requires that V in is greater than or equal to 0. If it's greater than or equal to 0, then the diode turns on. If it's less than 0, diode is off. So if V in is less than 0, diode is off. What is V out? Let me draw the circuit. And then you can tell me what V out should be. Diode is off, and because it is off, it is modeled as an open circuit. And this is V in, this is R. What should be V out in this case? If we look at the circuit, diode is open. If the diode is open, is there a pathway for current to flow through? Absolutely not. So what is the voltage drop across the resistor? It's zero. If the voltage drop across is zero, what does it mean for the voltage at both ends of the resistor? It's exactly the same. So V out is equal to V in. And that's it. V out is equal to V in. So if you apply V in minus 1, you'll obtain V out as minus 1. If you apply V in as minus 5, you obtain V out as minus 5. Does that make sense? So now tell me what happens if V in is greater than or equal to 0 volts. Diode is on. If diode is on, it is replaced with a short circuit. And V out is equal to what? What is V out if the diode is on? Anybody? Nobody?
Is it V in?
No, because that was the answer for the previous one. It would not. It's a good guess, but no. You're asking me, you're telling me. Okay, I like, you should have confidence. Yeah, it is V0. All right, fundamental concepts for everyone. We are measuring voltage between two nodes, and the two nodes are connected via wire. If there are two nodes in a circuit connected with a wire, then they are essentially the exact same node. If you try to measure the voltage between the two nodes, there is no difference in potential between the two nodes. Voltage is potential difference. There's no difference, then it's zero. So it's 0 volts. Okay. So let's take a pause, think over both scenarios, and let me know if you have any questions.
I'm confused on how it's zero. Is it because the positive and negative, there's like nothing in between, or?
It's because the diode is modeled as a short circuit. And if it's a short circuit, then it's simply a wire. And so there's a wire that joins both nodes together. So if we try to measure the voltage across the same node, electrically speaking, it's the exact same node. So if you try to measure the voltage between those two nodes, the difference would be 0 volts. And we can easily test this in the lab. Well, don't do this procedure, but I'm just, just saying this. So we have multimeters. These multimeters can measure 120 volts AC. If you stick it into a power outlet, not stick it, but if you measure the voltage at the power outlet, you would see it's 120 volts, give or take a few. But now you have parallel outlets at most extenders, right? If you take the multimeter and you measure the voltage between the two exact same terminals of two separate power outlets, you're measuring the exact same node. The voltage would be equal to 0. Would not be any different. So plus and minus of the same power outlet, you would get 120 volts. A plus terminal of two separate power outlets that are connected in parallel would be 0 volts. Does that make sense? Okay. All right. So now you think over what would happen if, actually, let me first draw out the output diagram. Before we go to the CVD model. This is the x-axis where you have V in. This is the y-axis where you have V out. This is the origin, 0, 0. V out equal to 0. Here, V out is equal to V in. Okay. This is a plot of the output voltage as a function of the input voltage, V out versus V in. V in on the x-axis, output on the y-axis. It is also known as the voltage transfer characteristic or the voltage transfer curve. Essentially, it is plotting voltage against voltage and is showing you how the input voltage is transferred to the output, hence voltage transfer characteristic. Or as we say in short form, VTC. Okay, VTC. So now that we have seen how to analyze the circuit using an ideal diode model, let's replace it with a CVD model. As I'm very fond of pointing out, the CVD model and the ideal diode model are very similar. They're exactly the same, except that it requires 0.7 volts to turn on. Right? In reverse bias is exactly the same. Forward bias is also the same, but it requires 0.7 volts to turn on. Once it turns on, it holds that voltage constant. And so we can model it as a short circuit in series with a voltage source of 0.7 volts. Okay, and that is shown right here. So in reverse bias, open circuit, no difference. In forward bias, it's a short with a 0.7 volt voltage source. That voltage source has a positive at the anode, negative at the cathode. And that's the only difference in the CVD model. So in the CVD model, if V in is less than 0.7 volts, diode does not turn on, it remains off. Actually, that does not look like D off, it looks like DOF. Diode D is off. And then if it's off, we can say V out is equal to V in. Okay. So again, in the CVD model, constant voltage drop model, diode requires 0.7 volts to turn on. If it's below that voltage, it will not turn on. It will remain off. And if it remains off, the answer is exactly the same as the previous one, meaning the ideal diode model. V out is equal to V in. Because there's no pathway for current to flow through. So question being asked is about V out is equal to V in. And it's there because it's an open circuit. There's no pathway for current to flow through. So there's no voltage drop across that. Does this make sense? All right. So now what happens if V in is greater than or equal to 0.7? Diode D turns on, and V out is equal to, what is V out equal to? 0 volts, 0.7 volts. And so then we obtain a characteristic that looks like this. This is on the left is V in less than 0 volts. And on the right is V in greater than 0.7 volts. Okay. So constant flat line at 0.7. Let's take a pause. Let me know if you have any questions. Any questions? By the way, yeah, go ahead. For silicon diodes, it's, well, in real life, it's between 0.6 to 0.7. So the question being asked is it universal? Is the value for the diode turn on voltage universal? The answer is yes and no. For silicon diodes, yes. So it based on the material that we use. If it's made out of silicon, it is between 0.6 and 0.7 volts. This germanium is between 0.2 and 0.3 volts. It's gallium arsenide, which is a compound semiconductor used for making LEDs. It is above 1.2 to 1.2 volts. So every material requires different turn on voltage. Okay. Also, in real life, that voltage is not quite constant, right? It has a slope like this. You see that slope? Right? So the constant voltage model is also an approximation because we approximate or we just assume that it's going to remain straight at 0.7. That's not quite the case. Okay, there is a slope to it. So it's not constant at 0.7. It'll start turning on around, let's say, 0.59, 0.58, 0.6, 0.61, 0.62 through 0.63, 0.64, and so on and so forth. And there's a slight curve right around there. Okay. But that is 2 quarters later in 315. Okay. We'll talk more about that in 315. Which there is a possibility that I might be teaching 315. So you can't escape me that easily. I did 315 in last spring, so it looks like I might be doing it again this coming spring. Anyway, that is semiconductors. That's where we learn about the details and how it's actually built and created and all of that. For now, all we are looking at is the two simplest models, which is ideal diode and CVD. That's all. I was going to point out that there will be a guaranteed question based on these on the final exam. So ideal diode model and or the CVD model will be on the final exam. Okay. And, the final exam page will be updated sometime around last week of classes, maybe during the Thanksgiving break. And so you'll have all the information you need to prepare for the final. Okay, let's move. It's 2:30, so we need more than 30 minutes to get through the next few examples. Okay, so here is a circuit, similar circuit to the previous one. I'm gonna analyze using, actually, wait, no, this is the exact same circuit. We are simply simulating an LT-SPICE. So, same circuit, simulating LT-SPICE. Now we're using a real life diode, 1N4001. So silicon diode, and you can see here, turns on around 0.6 or less. So there's a slight curve right here where it turns on, and it's not quite like a flat line. There's actually an angle to it. I'll erase these, and then you can observe. Do you see that? Look at the distance here, and look at the distance here. It keeps on increasing. Okay, so real life diodes, it's not a flat line. Okay, does not hold the voltage quite constant. There is fluctuation. Okay, let's see. In LT-SPICE, and I'm going to assign this for student practice. So it's the same, it's a computer simulation of the manual analysis we just performed on the previous slide. Okay. You assign DC voltage, you're going to vary that DC voltage from -5 volts to +5 volts in steps of 0.05 volts each, right? And you should be able to obtain this exact same transfer characteristic. All right. In our manual analysis, we assumed that diode turn on voltage was 0.7. In LT-SPICE, if we choose a particular diode, then that's turn on voltage is already built in. We cannot change it. Okay, we cannot change it. It is built in, so we cannot change it. All right. So it's 0.66 volts, and that's what you're going to see. All right. Before we move on, I want to ask you, what would happen if you flip the diode? Anode and cathode, you flip it. What do you think will happen? Let me draw the circuit for your convenience. And this is V out. And you can simulate this, vary it from -5 volts to +5 volts. And you can easily verify your own answer. But I would encourage you to first manually analyze this circuit using the CVD model, and then verifying it with LT-SPICE. And I'll tell you exactly what will happen. We have two cases, right? For ideal diode, V in is less than 0 and V in is greater than 0. So if the diode is flipped and V in is less than 0, is the diode on or off?
Off.
It is off, absolutely. Actually, no, for less than 0. Remember here, ideal diode model, diode is pointing down and V in is less than 0, meaning cathode is applied negative voltage, anode is applied positive voltage. So in this case, when the diode is flipped, the diode is on. And the same thing results In this case, diode is off. And because the diode is now flipped. Okay. Here, V out is 0 volts, and here, V out is equal to V in. This is using the ideal diode model. Students should do this with a CVD model. The two simulations to run. If you want more additional practice in understanding this, there are 4 combinations. You have a voltage source and you have a diode. You can flip the diode. So now you have 2 cases. Then you go back to the first one, you flip the voltage source. So now that's a 3rd case, and then you flip the diode again. So that's a 4th case. So 2 by 2 cross matrix. Okay. So do the manual analysis on your own and then verify it with LT-SPICE. LT-SPICE simulation doesn't take long, right? You just keep the circuit open, simulate it, flip the component, click run, and you'll see the waveform change automatically. Okay. Next. Same circuit, everything exactly the same. What the only difference is, we are now applying, instead of applying a DC voltage, we're now applying a AC voltage. In this case, we are applying a sinusoidal waveform. Sinusoidal waveform, meaning AC waveform, which is mathematically represented with a sine or a cosine function. Hence, it's known as a sine wave. The sine wave has a positive peak and a negative peak, right? Positive as well as a negative peak. You can see here the sine function is described going from 0 to 5. In the description, we only describe one peak value. Okay, that one peak value means it goes positive peak at 5 volts and it also goes negative peak at 5 volts. So it swings between plus and minus 5. Okay, plus 5 and minus 5. And then the analysis is transient analysis. Okay. This is known as transient analysis. All right. Transient, the word in the English language is fleeting, momentarily. Okay. This is also something you will study in 215. Charging and discharging of capacitors and inductors, which is transient analysis. Okay. All right. What do you think about the analysis? Far more complicated than simple DC analysis? Yes? No? The answer is no. It's exactly the same. Because the only thing we're concerned with, the absolute only thing we're concerned with is the diode on or is it off? And what is required to turn it on or off? That's all. We don't care what the waveform is. We don't care if the waveform takes 1,000 different or 1,000,000 different values when it's in the positive or the negative. All we want to know is whether the diode is on or off. That's all. So if we take the CVD model, which is I stated earlier, all the rest of the analysis is CVD model. What does it require to turn the diode on? V in must be either less than or greater than some voltage, right? So let's say V in is less than the diode turn on voltage. Ideal diode is 0 volts. Regular CVD model, let's say 0.7 volts. So if the input voltage is less than 0.7 volts, diode is off. If the diode is off, what is V out? We just saw it in the previous slides. V out is equal to V in. That's it. And so we obtain this waveform, which is the negative cycle, right? Now, input voltage is not shown here, but the waveform goes like this, right? This is the positive, just a rough, crude illustration, but positive peaks. Does that make sense? All we are concerned with is whether V in is greater than or less than the diode turn on voltage. If it's less than the turn on voltage, diode is off. If it's greater than the turn on voltage, diode is on. So if V in is greater than or equal to 0.7 volts, diode is on. V out is equal to CVD voltage, which in this case is 0.7 volts. And then the rest of the positive cycles are all cut or clipped. Hence, the circuit is also known as a diode clipper circuit. It's known as the diode clipper circuit. This level is 0.7 volts. If you look closely, actually, let's take a pause, think over that. Let me know if you have any questions. While you're thinking, just pointing out again, the analysis is exactly the same. The behavior of the circuit is also exactly the same. Yes. What do you think? No, I'm not laughing at you because you're ahead. We'll get to it. That was very good thinking on your part. I'm just chuckling that students are ahead. We instructors have to keep a little bit ahead of the students. But every now and then somebody does throws a curveball and we don't have an answer. So feel free to ask as many questions as you want. Okay. So far, so good. Right. So as I was saying, this is an LT-SPICE simulation. So it is using approximations to approximate a real life diode. So if you look closely at the surface right here, right, it's not a flat. It is not a flat. It's not flat because the voltage required to turn on and off is not a straight line. And so you'll see a slight curve when it turns on and off. All right. The other name for this circuit is there in the title. It limits the voltage to a certain level. Hence, it is also known as a limiter, diode limiter circuit. Clipper or limiter, same thing. And then as the question that was asked earlier, can we get a negative clipping circuit? And the answer is absolutely yes. All you got to do is flip the diode. And you get a negative clipper. And all we have done in this case is diode is flipped. And you get a negative flipper. So as you are practicing or reviewing these slides, please make sure that you're simulating the circuits in LT-SPICE and then explaining it to yourselves on how it is operating as a flipper circuit. All right. Okay, so the next one is interesting. All right. We will pause for a few seconds while you look at the circuit and you think over on what is required to turn the diode on or off, on and off. Oh, sorry. Need to close that. What do you all think? Any thoughts on what is required to either turn it on or off? Absolutely right. Yes. You gave the entire answer. Yeah. Anyone else? Well, I already confirmed that it is correct. So you're like 2 steps ahead. Okay. So the methodology here would be to look at the diode and see what is connected at its terminals. Okay. So what is connected at the anode and what is connected at the cathode? In this circuit, we have the cathode connected to plus 5 volts. So if the cathode is already at plus 5 volts, what does the anode need to be at in order for it to turn on? Anode needs to be greater by 5 volts plus 0.7. So the anode must be at 5.7 volts or greater in order for it to turn on. Below 5.7, it will remain off. Yes. Yes, it's not shown. Question being asked is V in is not shown. Yes, that is correct. So let me draw out the circuit with the terminals. By the way, so when you see circuits like these, this happens all too often in real life. There are circuits that are drawn like this because larger circuits, which comprise of billions of connections, like literally billions of transistors on one microchip, you can't even like visualize all of it at once. So you have multiple connections going all the way across, crisscrossing everywhere, right? So the way circuits are laid out, you could have a circuit like this, and you could have another circuit in a different part of your diagram where you just do this. And you'd say this is out, and this is perhaps out 2. And you can do this in LT-SPICE also. Okay. You can lay out individual components as they are and simply label them. If you just label them A, B, C, D, E, F, G, or whatever number you want to provide, or any names, notations, and then if it matches, LT-SPICE will automatically recognize that those 2 points are connected together. So if I was to lay out this circuit in one part of LT-SPICE and lay out this in a other part of the LT-SPICE, what do you think it would understand? First thing is, ground is the same. So it'll take those 2 points are connected to ground. Then if out is the same, meaning there's a connection from here to here. Okay. And so that's how it's laid out in circuits. Okay. So if I was to draw this out, this is how it would look. We have this is V in here, and this is V out here. We have this 5-volt source. So in the CVD model, what we need to look at is, well, not CVD model, sorry, in this circuit, we need to look at what is the voltage at the anode and or the cathode. In this case, cathode is at plus 5 volts. So in order for this to turn on, V in must be greater than 5 volts plus the voltage required to turn it on, which is 0.7. So if V in is less than 5.7 volts, the diode is not going to turn on. It remains off, and my V out is exactly the same as V in. Okay. V out is exactly the same as V in. Yeah. Yes. Yep. Just another way of stating the same thing. Yeah. If V in is greater than or equal to 5.7 volts, diode turns on, and V out is equal to 0 volts. Right? Does it make sense? Let's take a pause, think over that. I was testing to see who's paying attention. Five point seven volts. That was just pointed out earlier. This one student. Well, 2 students, I would say. All right, so enough with the jokes. Let's draw out the transfer characteristic curve. So it would be below 5.7, V out is equal to V in, and then above 5.7, it would be a constant. So this is actually plus 5.7 volts, and here V out is equal to V in. Okay. Student practice. Let's see how much 6 minutes left. I need to kind of rush through for the next one. Student practice. Flip the diode. Also flip the voltage source of 5 volts. Okay. All right. Let's go through the next one. Is the exact same circuit, but now with the added challenge of another diode connected in parallel. So if there's another diode connected in parallel, we have 4 states or 4 possible combinations. Diode D1 and D2 are both off. Diode D1 is on, D2 is off. Diode D1 is off, D2 is on, and both are on. Okay. In the CVD model, again, in any model, what we want to look at is how much voltage is required to turn it on or off, right? So, and this is going to go by a little bit faster. We already know if it's less than 5.7 volts, D1, let's call this D1. Let's call this D2. D1 is going to be off. We already know this from the previous one, right? How about D2? Any voltage connected at any end or either end of D2? What do you think? Look here, right there. The anode of D2 is connected to ground, meaning 0 volts. So anode is held at 0. So in order for the diode to turn on, the cathode must go below 0.7. Okay. So if it's 5.7 or above, or any value, diode is going to be off. So if it's less than 5.7, we're going to say diode D2 is also off. And V out is equal to V in. Okay. V out is equal to V in. But there is a limit on that negative voltage, right? We just said that the anode of D2 is at 0 volts. In order for it to turn on, the cathode must go below minus 0.7. The cathode must be less than minus 0.7 or in order for the diode to turn on. Okay, so a subset of this first is if V in is less than minus 0.7 volts, D1, of course, is going to remain off, but D2 will turn on. Okay. D2 turns on, and it's modeled as a 0.7 voltage source. And V out, of course, is measured with positive here, negative here. Hence, V out becomes minus 0.7. That's the only difference. And third, V in is greater than 5.7 volts. Then D1 turns off. I mean, D1 turns on and D2 turns off. V out is equal to 5.7 volts. So here's like this. Oh, there goes the bell. This is minus 0.7 volts. Okay. All right, let's take a pause. Let me know if there are any questions. Yeah. That's not possible. That is correct. We can still analyze the circuit based on that way. So those are the methods that we haven't looked at here. That's something we reserve for like 315. But it's, yeah, it's a very good question. So the observation made or the question being asked for confirmation is, can D1 and D2 both be on at the same time? The answer is no, not for the way the circuit is configured. Both D1 and D2 cannot be on at the same time. Yeah. Absolutely. You can change the voltage source, which is the 5-volt source. And if you change the value, then the output voltage changes. That is correct. Not like an op amp, but your main point still is correct. You change, so the question being asked is if we change the voltage here, does that mean that this changes? The answer is yes. Yeah, we can different points of the wave. Meaning if we apply a sine wave input, like an AC waveform, different value at a different point. Meaning if this, instead of being DC, if this was AC. Is that what you're saying? So yes, yeah, it would work like a comparator kind of thing. Yeah. But it would simply be, you have two varying inputs. You have one varying input here, another one here. So it just depends on how and what their voltages are. But yes, the answer is yes, it is possible. Okay. Any other questions? All right. Okay, we'll end class here today. We'll see you all on Friday.